Hello, and welcome to our group's presentation. We are Project CHROMA, which stands for Color Harmonization from Skin Tone Recognition with Optical Monitoring for Adaptive Lighting in Entry-Level Photography.
Our team consists of myself, Matt Cope, Juanita Solania Romero, Juan Trochinsky, and Nikul Patel. The spark for this project came from an acquaintance and professional photographer, Lee, who mentioned how difficult it is to accurately photograph performers with dark skin under stage lighting. Once the sun goes down or people are inside and away from natural light, cameras have a hard time capturing dark skin tones without them being washed out.
To solve this issue, our group created a lighting system to throw the correct colors of light onto subjects to ensure accuracy when they are photographed. And here we have a high-level diagram as to what our system looks like, with our 3 light panels and the ICU focusing on a single person's face. The following 3 slides discuss our project goals and their corresponding objectives. Here we have our basic goals, which is how CHROMA functions on its most basic level. So here we have our central control unit, which we are calling the image capture unit, which is the brains of the system. It is able to house the lens design as well as the programming that will detect someone's skin tone and then communicate that data to a light panel. Now these were the advanced goals of our project, meaning that once we got with the basic function of our system, this was finer tuned details that we wanted to add on top, which would be creating an additional panel that works independently from the other and design housing for the light panels and the ICUs themselves, as well as to have a response time of under a minute, meaning from the start of the system analyzing someone's skin tone to the finishing of the lights actually changing automatically. That's what we are timing, and we're trying to get that in under a minute. These are our stretch goals, which means they're goals that we set forth, understanding that while time is limited, they would be nice if we accomplish them within the span of Senior Design 2. As a reminder, this is our specifications table. As you can see, it is broken up by each subsystem. And our 3 key dimensionables for the project are in white boxes highlighted with yellow.
In this hardware diagram, it shows how the system will operate, and to the right-hand side are all our legends signifying who is working on which subsystem and what each of the arrows mean. As seen here, the information needed is taken by seeing the subject with the use of our image capturing unit, labeled here as the ICU, and relaying that information to the light adjusting PCBs that I will talk about later. This PCB will then help control the fill light boxes that will be made to then shine the correct brightness, temperature, and color of the light onto the subject.
Our software system begins when the Raspberry Pi captures a live video feed using the Pi camera. Each frame is analyzed to detect if a face is present. If a face is found, we extract the RGB value specifically from the forehead region, which we found to be the most consistent under lighting. These RGB values are then compared against a CSV dataset of predefined skin tone samples based on the Monk skin tone scale. After collecting 7 samples, we compute the most frequently occurring match and classify the skin tone accordingly. Once the skin tone has been determined, our program maps that tone to a corresponding lighting preset labeled as buckets, which are pre-programmed in each ESP32's WLED configuration. The Raspberry Pi then sends an HTTP GET request wirelessly to each of the ESP32 microcontrollers connected to the LED panels. These ESP32s act on the API command. This triggers the matching lighting presets for all connected LED panels in sync. Additionally, when the system is reset, the Pi sends the boot preset to all devices. This base lighting provides a uniform illumination for reliable skin tone sampling during the next cycle.
We will now discuss the design process of the different subsystems that are part of CHROMA.
For this project, we needed a microcontroller unit, also known commonly as an MCU. The main requirements for our MCU were that it be affordable for us to purchase, as we would need at least 3 of these. The MCU also needed to have Wi-Fi and Bluetooth capabilities, the ability to use UART and I2C, an analog digital converter, and other specifications we go more in depth in our paper. As you can see here, the ESP32 was one that fits our needs the best, as it has all the requirements we needed with all the added benefits of having a dev board for this specific MCU to do tests on. This also was a very suitable MCU for us, as many of us already had ESP32 dev boards with us to do testing on, which reduced the overall cost of this project.
For our project, selecting the right single board computer was essential to ensuring smooth real-time processing while keeping cost and power consumption manageable. We compared 5 different options: NVIDIA Jetson Nano, Google Coral Dev Board, Odroid, Upboard, and the Raspberry Pi. Our evaluation focused on key specifications such as CPU, GPU, RAM, storage, and built-in connectivity like Wi-Fi and Bluetooth. We needed a board that could efficiently handle our machine learning model for skin tone detection while maintaining low power consumption. The CPU and RAM had to support real-time processing without excessive lag, and dedicated GPU was a plus for image processing tasks. In addition to performance, we considered hardware integration. Built-in Wi-Fi and Bluetooth would streamline communication between the system components without requiring extra peripherals. Storage flexibility was also important for hosting datasets and model files, as those can get really large. Lastly, affordability and developer support played a major role in our decision. A strong software ecosystem with active community resources was key for troubleshooting and long-term viability. After looking at all of these factors, we found that Raspberry Pi was the best choice for our project. When selecting a machine learning framework for this project, our primary focus was on efficiency, compatibility, and real-time performance. Since the Raspberry Pi is a resource-constrained device, we needed a framework that is lightweight and optimized for image processing without requiring a dedicated GPU. This led us to compare OpenCV, TensorFlow, and PyTorch, evaluating their suitability based on factors like cross-platform compatibility, pre-built image processing tools, and overall system performance. A key requirement for our system was built-in support for face detection and skin tone analysis. TensorFlow and PyTorch are widely used for deep learning applications but are computationally intensive and often require hardware accelerators like GPUs to run efficiently. While TensorFlow Lite offers optimizations for embedded devices, it still introduces additional processing overhead. PyTorch, on the other hand, is primarily designed for research and experimentation, making it less ideal for our real-time applications on the Raspberry Pi. Ultimately, OpenCV emerges as the best choice due to its optimized computer vision algorithms and built-in face detection capabilities. It allows us to process images with minimum latency, enabling the system to dynamically adjust lighting based on detected skin tones. Additionally, OpenCV's strong community support and extensive documentation make development and troubleshooting more efficient. This framework provides the right balance of speed, accuracy, and resource efficiency for our project's needs.
When building an imaging system, the sensor selection is the first step, since this is what determines many of the important parameters. However, my optical components hinge upon being compatible with our hardware and corresponding software capabilities. Because our team decided to use a Raspberry Pi for the ICU, I could only choose a sensor that was suited for the Pi. Therefore, we looked at Pi cameras. Now, part of the reason we chose this model was because of its sensor selection. So for the scope of our project, I went with a high-quality camera, since the sensor size allowed for versatility in field of view and focal length. Many others came with lenses already built in, which would interfere with the lens design. Now, with the lens design, we are creating a telephoto objective that combines a large positive and negative lens. The positive lens is there to collect as much light as possible into the system, while the negative lens will magnify our image so that we capture our subject's face and neck clearly. Since CHROMA focuses on color, I need to ensure that the chromatic aberrations were reduced while also remaining in budget. There are a few ways to do this, namely an achromatic, apochromatic, and super achromatic system. An achromatic system corrects 2 wavelengths, while apochromatic corrects 3, and super achromatic 4. The cost goes up significantly as more wavelengths are corrected. So we went with an achromatic system, and while only 2 wavelengths are corrected, red and blue, this suits our needs since these are the wavelengths we will be focusing on.
In selecting our LED technology, we looked at the wide variety of LEDs available across the market, including single color, bicolor, meaning 2 different shades of white, RGB, red, green, blue, assignable RGB and RGB integrated circuit, RGB white and then warm white, and then finally RGB CCT, standing for correlated color temperature. All of these have their own pros and cons, but ultimately we ended up deciding on the RGB CCT as those have the trifecta of what we need, meaning they are tunable in color, they are tunable in their white color temperature, and they output a broad white spectrum, which is absolutely necessary to ensure accurate photography. Upon selection of CCT as our LED technology, we were able to find a few options for hardware, from super bright, super lighting, and waveform technologies. We selected Waveform's 5-spec film grade LEDs as they offered everything we were looking for: a high color rendering index, high LED density, and a controlled beam angle. Additionally, they were the only company to offer full photometric reports for all of their products. This was key as we were able to actually see what the difference would be between their cool, daylight, and warm light temperatures. In our research, we found that the skin reflectance across all skin tones spikes around 630 nanometers. This corresponds to the reflectance spectrum of human blood, as the light bounces off the blood vessels just beneath the skin. If the light does not have enough deep red, a person can look washed out, or even can look green due to the spike in green from hemoglobin absorption. The CRI value R9 corresponds to this deep red, and therefore was a priority when selecting our LEDs to ensure we would get this dark red.
To achieve our goals and create an imaging system that's in concordance with our specifications table, I have the simulation down below. As we see here, we have a positive plano-convex lens that has a 3-inch diameter. It is for collimating, and its large aperture allows us to gather as much light as possible even in low light conditions. The second lens is a negative lens, which is a plano-concave with a 2-inch diameter, and that is primarily for magnification of the image to ensure that we are fully capturing one's face, and it is focused specifically on that so that the model is able to run properly. And the last lens is technically 2 lenses. It is an achromatic doublet, which corrects for chromatic aberrations, which is what we are focused on, especially with the system, as we want the colors to appear as true to life as possible and reduce those aberrations. So to achieve all of this, we're able to meet the specification of a vertical field of view of at least 20 centimeters to be able to capture someone's face, and we have a working distance of 6 to 12 feet. And as you will see in the next slide, the lenses are able to shift along the optical path and be able to be refocused easily so that it's very adaptable and flexible to a photographer's needs to a specific situation. This is the housing for the ICU. There are 4 sections, one for each individual lens, and then the Raspberry Pi plus the sensor. The design for the lens mounts and tubes are all the same, just adjusted to fit the diameter of the lens and the distance it can or needs to travel. The tubes are interchangeable, so depending on how the photographer wants to set up, they can put each mount into whatever length tube is needed. The stationary tube holds the lens mount upright, and centered on the optical path and the sensor, while the translation tube spins from the outside and rotates the lens, moving forward and back and adjusting the horizontal position of each lens. Our stands are also adjustable by height, moving an additional 10 centimeters off the tabletop. This is our field of view testing. As you can see here, the ICU is set up and we are focused on a 20 by 20 square across the way. We are about 11 and a half feet, almost 12 feet away, so at the very edge of our working distance capabilities. And that is the 20 by 20 square that we are focused on. Since a face is on average 20 centimeters long, we want to make sure that we are able to capture a full face in frame. And the center where we are focused on is fully clear. Here are some additional images taken during the testing of the ICU and its field of view. The top images, as you can see here, are of a working distance of 9 feet, and we are still able to fully capture our subject's face. The bottom images show a pink 25 by 25 square, and as you can see, it is fully in frame, and this is from a working distance of about 7 feet, further confirming that our field of view specification is being met.
Our software is designed to process and classify skin tones in real time by leveraging multiple Python scripts and libraries like OpenCV, face recognition, and NumPy. A Raspberry Pi runs the software using a Pi camera module for image capture and MQTT for seamless communication with the lighting system. The dataset we use significantly reduced the time needed to train by providing a diverse set of labeled skin tone images. To ensure accuracy, we standardized image sizes with my resize images script, extracted RGB values from faces with my model training script, and used my facial recognition script to detect and classify live skin tones against the dataset. This system allows for real-time adjustments to the lighting setup based on detected skin tones, optimizing illuminations for diverse subjects. Our real-time facial recognition system successfully detects and classifies skin tones using OpenCV. The facial recognition script processes live camera feeds identifying faces and extracting RGB values from the forehead region for accurate skin tone classification. These values are then compared against the Monk Skin Tone CSV dataset, allowing the system to determine the closest match. Importantly, the test subjects used in our demo are not included in the training dataset, demonstrating the model's ability to generalize across different individuals. By dynamically assigning skin tones labels, this system enables precise lighting adjustments, improving image quality across diverse complexions. The dataset processing and model training stage is crucial for ensuring our machine learning model accurately classifies skin tones. To maintain consistency, we first standardize all images using the resize images script, which resizes and formats them uniformly. Then, model training script extracts RGB values from the forehead region of each subject in Google MSTE dataset and stores them in Monk Skin Tone CSV file. This dataset contains around 11,000 labeled RGB values, saving us significant time by providing pre-labeled skin tones samples, allowing our model to be trained efficiently without requiring manual data collection. This structured dataset ensures real-time performance and improves the accuracy of the skin tones classification on the Raspberry Pi. For our wireless communication, we use a local Wi-Fi router not connected to the internet to wirelessly bridge the Raspberry Pi to our ESP32s. The Raspberry Pi performs face detection and classifies a user's skin tone in real time. Once a tone is identified, it maps to a lighting preset, and the Pi sends an HTTP GET request to each ESP32 over the local network. The command line follows the WLED API format preset load equals X, where X is a preset ID. Each ESP32 then activates the corresponding LED preset synchronously, ensuring consistent lighting across all devices.
The schematic for a PCB design that will go into our lighting panel and control the high CRI RGB CCT LEDs. Outlined in blue are the major sections of importance for our schematic. On the right-hand side is the ESP32 and its boot button by its right, and enable button to its left. The ESP32 utilizes a UART bridge to allow us to flash the MCU with WLED, In our case, on the left-hand side, we have the CP2102 UART bridge. The other major components on the schematic are the IRLZ44N MOSFET transistors that allow us to control the pulse-width modulation, or PWM, of the LEDs that we are using. To power the ESP32, this schematic was made for a regulator board, which helps step down 24 volts we are using for the LEDs to 3.3 volts to power the ESP32. We're using an LM2576 regulator to lower our voltage from 24 volts to 5 volts, and we're using an AMS1117 to lower the 5 volts from the LM2576 down to 3.3 volts. Adapted from the schematic shown here on the top left is the drawing of the PCB made using KiCad. We optimized the layout of all components on the PCB to minimize space utilization while ensuring adequate spacing accommodating trace routing. Through-holes were added onto the PCB to allow us to use wires and couplers in our system, which provides us with the added benefit of keeping the board modular for maintenance and ease of use when needing to switch components or program our ESP32 MCU. On the bottom left is a fully built version of the main PCB. Made using the schematic, a regulator board drawing is shown on the left side. As mentioned before, it utilizes the LM2576 regulator and the AMS1117 regulator to get our desired voltage output. On the right side is a fully completed version of our regulator board.
For the design of the LED panel, we determined a size of approximately 230 millimeters by 120 millimeters would be correct for our objective. Each panel contains 96 chip-on-board LEDs. I designed reflectors on each side as well as having corners to minimize the light leakage. In the design process in Zemax, we eventually determined the reflectors would have an optimal angle at 60 degrees to ensure all light is reflected outwards. Shown here are the initial prototypes of the LED panel. First, we have the 5-channel LEDs utilized in the midterm demo applied to the metal backing to ensure that the full LEDs would fit. The second photo shows my 3rd generation of reflector design modeled out of cardboard. The third photo is the same reflector with an aluminum foil applied to test the reflectance angles. To construct the reflectors, we chose steel sheet metal for our material as it was available on hand. I hand cut all of the reflector parts with a Dremel and metal cutting discs, then used multiple polishing compounds to bring each piece to a mirror-like finish before assembly, as shown here by this time-lapse. This process was time-consuming but rewarding, as I could really see the difference in reflectance at each stage of polishing. Shown here are the finalized reflectors after being cut and polished, and the final iteration with full framing and the diffuser panel applied.
Now, we are able to change the preset operation, so I've changed it to our boot. Then we've got the individual buckets for each of the skin tones. As you can see, the LEDs are changing depending on the preset, generally going warmer for darker skin tones.
As with any design project, there were challenges that we faced and overcame. Some of the challenges are shown below, including that a full face alignment caused skin tone mistakes with our machine learning model, meaning that when someone was looking straight on into the camera, the model was more likely to inaccurately assess their skin tone. We tested a 3/4 angle and it increased our precision significantly. So now we understand that with the model how it is and with our camera that it is best to have our subjects slightly turned so that we get more of their side profile and able to capture their skin tone a bit better. Another issue we faced was that there were spherical aberrations and alignment issues which caused haziness in the edges of the images. Now, edits were made to the housing design to make sure that each lens was perfectly straight and on the optical path so that there wouldn't be any variance in angles, but it is made of plastic. There wasn't a 100% tolerance of all of these issues, but overall, the spherical aberrations and the haziness that's caused by these issues are not affecting the performance of our system. We are still able to view the center of the image, which is where our subject's face is going to be perfectly, and are able to have the model assess it with precision. Now, the last main issue we faced was that there was issues with our regulators since our LEDs are powered by 24 volts and we needed to step them down to 3.2 volts for the MCU on the same PCB. Now the electrical design was reworked, and instead of having a singular regulator bucking down from 24 to 3.2, there are multiple regulators now doing that same job. This is the bill of materials for our project. Now these prices do not reflect the prices including shipping, but even with that, we are well under our maximum estimated budget of $1,200. The work distribution for this project is separated into primary and secondary roles. As you can see, each person's primary role corresponds to their academic focus. Mads oversees the panels themselves, their construction, configuration, and the lighting control algorithms, which are based on skin tone. Juan programs the software on the Raspberry Pi and the MCUs, which include the image processing, machine learning model, and communication between the ICU and the panels. I am creating the optical system which will feed the input to the Raspberry Pi, as well as the housing for the entire ICU. Nicole is responsible for the electrical components, primarily PCB development, wiring, and soldering. The secondary roles, highlighted with orange bullet points, are a method to keep everyone on track. Some are outside the scope of the individual's knowledge, but we are aiming to understand all roles in this project, even if it is only at a simpler level. The CHROMA team thanks you for your time and consideration, and we hope that you enjoyed our presentation.